Welcome to Math 31. This is an exercise on rational inequalities. Previous lesson was on quadratic inequalities, and as you see that these solve in much the same way. In fact, the method is identical, and maybe one or two things we need to be aware of, but otherwise the same method. So let's start right up then. A rational expression would be basically a fractional expression. So when you get something like this, x plus 1 over x minus 3 less than 0, we got the same number line grid, and we're going to do the same sort of interval analysis that we did previously. Now, before we get too carried away with all this, let's be aware that we have a restriction based on the denominator. X cannot be equal to 3. That may or may not come into play later on. And otherwise, because we have more than one factor that is making up the inequality, we need to do the same thing. We need to break it into x plus 1, one factor, and identify its sign, and then x minus 3. And then together, we compare them with the function itself. Because with quadratics, you are multiplying the factors together. Here, you're dividing the factors, but it really does mean the same thing. So for x plus 1, the 0 for that factor is negative 1. And it doesn't matter what order you deal with this, but any x value larger than negative 1 will make that factor positive. You do it factor by factor, and then at the very end you look at them together. And then for the other, the 0 for x minus 3 is 3, and that factor will be positive for all values of x greater than 3, but then negative for all values less. Taking these together, f at x will be positive, because a negative divided by a negative is positive, and then in the middle interval it will be negative, and then for the interval above 3 will be positive. And we want to know where this one is negative. And so it will be negative, that is below 0, from in the interval negative 1 to 3, open. So the thing of it is, want to be aware that the fact that x cannot be equal to 3, that we had that restriction, it doesn't really enter into it because it was this open interval. X will never be equal to 3 anyways. So I'll just keep it like that. But that isn't a guarantee. If you have a closed interval, you will have to take into consideration any non-permissible values. Next one, 2x plus 1 over x minus 5. And here it's less than 3. And we do what we did for the quadratics, that we have it taken over set to 0. So this becomes 2x plus 1 over x minus 5. Subtract 3 is less than 0. And unfortunately, because you're subtracting two fractions, even if they're rational expression type things, we need to find an LCD and add them together. And by the way, x cannot be equal to 5. Either note that now, which is best, or if you forgot it, then do it later. But you need to recognize that. Now our common denominator is x minus 5. So the first factor, the numerator, is 2x plus 1. And then 3 would need to get multiplied by x minus 5. So carefully we work that one out. And we keep it in that form. That's typical all over the same denominator. So 2x plus 1 minus 3x plus 15 all over x minus 5 is less than 0. So this becomes minus x and then plus 16 over x minus 5. If you preferred, you could write that as 16 minus x. I'm not going to worry about it, but I am certainly aware that because we have the negative x factor, that may have an effect on our signs. So our first 0 is negative x plus 16, or 16 minus x, and then x minus 5 for the other one, and then together this is f at x. Now negative x plus 16, if you have any doubts at all about the sign, set it to 0 and solve away. And x, the 0 will be 16. So that's where we get the experience the sign change. And then x minus 5 will have a 0 at 5. Now with care, pick numbers bigger than 16 and see what happens. So if x was 17, it becomes negative 17 plus 16. And you see again that we're negative when we're to the right of it, and then positive to the left. But always be careful with it. You don't want to make a mistake with that. And then x minus 5 will be positive if x is greater than 5. And then negative if it's less. And then the function taken together, positive divided by negative, is negative there, positive there, negative there. And we want to identify where this thing is less than 0, that is negative. So it would be the interval negative infinity to 5, open, in union with 16 upwards forever, positive infinity. So that's a fairly common example. Number 3, x squared minus 1 over 5x, is noteworthy simply because we're going to have 3 factors. We have a quadratic on top. We are aware, I hope, that 5x cannot be 0, so x cannot be 0. So we do have a restriction, and it might matter because this one is given as an inclusive interval. Now x squared minus 1 will factor into x minus 1, x plus 1 over 5x. So the rule basically is that any factor that affects the sign has to be accounted for. So I'm going to write this, and it doesn't matter what order, x minus 1, x plus 1, 5x. These 3 factors make up what I will call the function f at x. And then identify the signs for each of the factors. Once again, pause me and go through this question, and then check your answer afterwards. Nice idea. So this first factor, pretty conventional. If x is bigger than 1, it will be positive, and then negative if it's less. X plus 1. If x is bigger than negative 1, it's positive. If x is smaller than negative 1, it's negative. And then 5x, its 0 would be right at 0. So if you set that to 0, you would get 0. And if x is greater than 0, say 1, it's positive. If x is smaller than 0, the whole thing is going to be negative. Carefully work out the signs. The 3 negatives will make f at x negative. And then between negative 1 and 0, negative and negative would become positive. Then between 0 and 1, it's negative, and then positive up there. So we want where it's greater than or equal to 0, that is where it's positive. So our intervals are going to be from negative 1 to 0. Now this normally would be inclusive, but we cannot be equal to 0, so we have to make sure we identify it with the open, or in this case the half open interval. And then this will be in union with positive 1 closed all the way upwards forever. So be careful with these ones. First off, you have 2 intervals, and second off, making sure that you pay a close attention to the restriction on the denominator. Number 4 is interesting for a couple reasons, and a few things you need to be aware of. Now, x squared plus 1, if you try to find a 0 or even an inadmissible value, you will run into a problem again because x squared cannot be equal to negative 1. And in fact, x squared plus 1 will never be equal to 0. It also will never be negative. So it's like when we saw for the previous. The other thing of note is this negative 2 on top. And normally you only include factors with a variable. I'm going to put the negative 2 there because it does affect the sign. And then I'll keep x squared plus 1 as is and call the whole thing f at x. Now, negative 2 does not have a sign change. It is negative everywhere. Now, if that had been just a positive number, we could have ignored it. But because it's a negative, we have to be aware that it changes the sign. And also note that x squared plus 1 is always positive. So it means that this entire expression is going to be a negative numerator divided by a positive denominator, which means the function is negative everywhere. So that means that the answer is negative infinity, all real numbers, all the way up forever. So kind of a special case. Now, number 5, not much going on with this one. I think, in fact, that I won't bother going through this one just because it's kind of redundant. Save you a little bit of time. Number 6, though, has got some things going on. Now, it must be factored. You have to factor, as we saw with the quadratics. In this case, we must factor the numerator. And if we factor it, we can take out a factor of x or negative x. I would encourage you to take out a negative x to keep both these other terms positive. This becomes 3x plus 1 divided by x plus 1. And this is supposed to be greater than 0. Now, our factors are negative x, our 3x plus 1, our x plus 1. So anything that's there that affects the sign, so that would be anything but just a positive number, we keep. And then the zeros for each of them. Mostly you can tell by inspection. Like negative x, the 0 is 0. You set that to 0, that's what you get. And by the way, x cannot be equal to negative 1. Be careful, though, with the sign of that factor, negative x. If x is positive, if bigger than 0, then negative multiplied by a negative factor, it becomes negative, just like it'll be positive to the left. So that's one of those we need to be careful with. 3x plus 1, the 0 is negative 1/3. And if you plug in an x value bigger than negative 1/3, say 0, then the factor does become positive. If you plug in an x value less than negative 1/3, it'll be negative. X plus 1, the 0 is negative 1. It will be positive, that factor will be positive for all x values greater than negative 1. And then negative to the left. So now your negative times a negative, or divided by negative, with the two negatives makes the function positive there, makes the function negative there with the one negative, positive there, and then negative there. And we want to find out where it is positive, greater than 0, so there and there. So the interval would be to the left forever, all the way up to negative 1, open, in union with the interval from negative 1/3 to 0. So every factor that makes up the rational expression has to be accounted for. Number 7, x plus 1 over x squared minus 3. Well, for restrictions, if we go x squared minus 3 is equal to 0, x squared is equal to 3, or cannot be equal to 3, so x cannot be equal to plus or minus root 3. I'll keep it as an exact value, but it's like a 1.7 or something like that. Now, with respect to these factors, we have another issue here. The one factor is x plus 1. Now you could keep this as x squared minus 3 throughout, but it's a bit of if you do that, you need to be aware that there's two zeros associated with it. So what I'm going to do is I'm going to take this x squared minus 3, and I'm going to actually factor this as x minus root 3 and x plus root 3. And that way I've got two factors. Now some of you would decide that's not necessary, and that's okay. But it does remind me that there are two factors, there's two zeros, there's two sign changes. And really this whole method is to minimize the amount of note and record keeping you have to do yourself, and you let the numbers take care of themselves. So our zero with x plus 1 will be negative 1. That's where the sign changes. So if x value is bigger than negative 1, we'll make this positive. X value smaller than negative 1 will be negative. Now x minus root 3, well, that would be, set that to 0, and we get a 0 of square root 3. So if you pick values bigger than root 3, say 2, you'll get a positive number. 2 minus 1.7 is positive. And the same true in the other direction. Now, I didn't really draw this too proportionally, but I'll manage. X plus root 3, if you set that to 0, you will get the 0 to be negative root 3. So if you picked a value for x, say 0, we don't get anything strange happening. It's positive to the right and negative to the left. So that means, a little tight there to the left, but a negative, 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 three negatives will mean that function is negative there. Two negatives makes it positive. This is negative there, this is positive there. So we want where it is negative. So we want there, we want there. So this means that this is going to be negative from negative infinity all the way up to negative root 3. Now be careful, because even though this is given as an inclusive interval, we cannot be equal to negative root 3. So we have to keep that open. And this will be in union then for the next interval is from negative 1. Now negative 1 we can be equal to, so I'll fix that up, all the way up to positive root 3, but not being equal to it. Number 8. This one you might want to do on your own. Nothing too strange happening here. X cannot be equal to 0. The numerator, don't forget to factor it properly. 1 minus x, 1 plus x, and then 5x for the denominator. One minus x, you probably don't need to see this one. Pretty routine. List all the factors. 1 minus x will have a 0 at 1. 1 plus x has a 0 at negative 1. 5x, the 0 is right there at 0. So 1 minus x, if you picked an x value bigger than 1, you'll get negative to the right and positive to the left. For 1 plus x, pick an x value bigger than negative 1, it's positive. And then negative to the left. For 5x, pick an x value bigger than 0, and that's positive. And then negative to the left. So therefore, this function will be positive to the left of negative 1. It will be negative there, with the 1 negative, positive there, then negative. And we want where it's negative, so at this point, Hopefully you're getting comfortable with the operation. It'll be an open interval, so there's no issue with the restriction from -1 to 0 in union with 1 to everywhere upwards. Now two more, let's go through these ones. That one was straightforward. This one's a little bit more complicated. Now, with this denominator, we have two factors down there. And that means when we solve them, or when we look for restrictions, we have to be careful, because 6x cannot be equal to 0, so x cannot be equal to 0. Same thing is true with the root of x plus 1. Now, it's true that this cannot be equal to 0, but in fact, it's more so than that. If you think back to domain and range, x plus 1 has to be greater than 0. You can't have a negative, or it cannot be equal to 0. So x has to be greater than -1. So we actually have kind of an awkward looking domain. X is greater than -1, and then it cannot be equal to 0. As well, that numerator will factor into 1 minus x times 1 plus x. And then the denominator is 6x root x plus 1. And we want where this thing is negative. So I'm going to list each of the factors. 1 minus x, 1 plus x, 6x, and then root x plus 1. Now the 0 for 1 minus x would be 1. We've seen that many times, or a few times at least. 1 plus x, the 0 will be -1. 6x, the 0, is going to be 0. And then we have to deal with that root of x plus 1. Well, the thing of it is, this doesn't even exist to the left of -1. So that factor is equal to, right at x equal -1, it's equal to 0, but we're not going to the left of it, so there's no sign change. So the rest of it is just a matter of working our way through these ones. 1 minus x will be negative to the right of 1 and positive to the left. 1 plus x, well, it'll never be negative because we're never going to be, the graph does not exist when x is less than -1. So it's positive everywhere it exists. 6x does have a sign change at 0, positive to the right, negative to the left. And then the root of x plus 1, well, that's the positive root, so it's positive for all x values where the graph is defined. So then we take a look, and from -1 to 0, we're negative. We're positive in the next interval, then negative. And we want where it's negative. So we're going to be non-inclusive from -1 to 0, open interval, in union with 1 all the way up forever. So a little bit more complicated. That would be considered a challenging problem. One more, find the domain of this. And the way this works is the domain, if you think back, we isolate the y, which we've done, and we have to be aware that really this question is dealing with x minus 4 over x plus 1 must be greater than 0. So where is this function greater than 0? Because you cannot take the square root of a negative. We also cannot greater than or equal to 0, I guess. We could have this thing equal to 0. And we note that x cannot be equal to -1. At that point, it becomes easy enough. Pause me, please, and go through this one. X minus 4, x plus 1, f at x. Our 0 is at 4. Our 0 is at -1. If x is bigger than 4, that factor is positive, and then negative to the left. As for x plus 1, it would be positive to the right of x plus 1, negative to the left. So this is, and then f of x would be positive, negative, positive. So where is this positive? There and there. Now be careful. Negative infinity to negative 1, but we cannot be equal to negative 1 in union with, well, it can be equal to 4 upwards forever. So that should take care of this. That's a challenging unit or lesson, and that will take care of the inequalities. And then following this will be a review of some factoring methods. So thank you for your time.